give a talk here at this seminar. And if you have some urgent questions during the talk, I'm also happy to take them. So today, as Tamara said, I will talk about dichotomy of the atmospheric circulation on TRAPPIST-1e. This work has been done in collaboration with people listed here, and in particular with the UK Met Office. So the questions I'm trying to answer in this study are the following. What model parameters, what GCM parameters can tip the atmospheric circulation into one regime or another? Are initial conditions important for these kind of simulations? What is the mechanism of regime bifurcation? What causes very low night-side surface temperature in one of the regimes? And is the amount of water vapor and clouds in the upper atmosphere affected by regime transition? And how, and does it show in observables such as transmission spectrum? To answer these questions, I will go through the following sections in my talk. First, I'm going to briefly talk about some fundamentals of atmospheric circulation on telelocked exoplanets. I will then talk about the dichotomy emerging in our GCM simulations of an Earth-like atmosphere of TRAPPIST-1e. I will particularly focus on the emergence of these different regimes during the spin-up of the model, and also talk about the decrease of surface temperature on the night side, which produces a very large day-night contrast in the simulations, and then talk about transmission spectra and terminator asymmetry in these simulations. So first of all, as many of you know, atmospheric circulation on tidal-locked rocky exoplanets has distinct features and differs from the familiar to us circulation on Earth due to various factors, such as the type of the star we orbit, the time and zonal distribution of stellar forcing on the atmosphere, rotation rate, and of course the atmospheric composition. And compared to the Earth, the rocky exoplanets that we usually study with GCMs are frequently found around M-dwarf stars, so their spectrum is quite different. They also have perpetual day and night sides, so perpetual forcing and stationary forcing, and their rotation rate is often larger than that of Earth, so it's often much larger than 24 hours. And atmospheric composition is unknown yet, but hopefully will be known soon with the successful launch of JWC and other future generation of telescopes. As I just said, the radiative forcing for tidal-locked planets is stationary and zonally asymmetric. As you can see from this schematic from Woodward's and Kreidberg view, you see that the stellar forcing affects the produces energy input for the atmosphere at the on the day side and energy output on the night side, broadly speaking, which then produces day-night temperature contrast, which forces the generation of overtonic circulation, which can be schematically depicted as here from Helm and Lewis paper 2021. This overtonic circulation has an upward branch at the substellar point and downward branch at the interstellar point. However, this vertical motions and associated divergence leads to the formation of stationary waves, which are depicted by these green arrows in the picture. and stationary waves accelerate zonal wind at the equator because of the eddy momentum flux, and produce atmospheric subrotation at the equator, which is shown by this red circle. And at the same time, the subrotating jet can shift and interact the planetary scale stationary waves. So this circulation has some similarity with the circulation in the tropics on Earth. On Earth, we know that the latent heat released by deep convection over the Pacific leads to convergence in the lower troposphere and divergence in the upper troposphere, and induces Rossby and Kelvin waves, which are schematically depicted in this bottom right picture from Valles 2020. So we have Rossby lobes to the west of the heating and Kelvin waves to the east of it. They also have their own properties, such as the different direction and speed of these waves, which can then interact and drive the momentum fluxes to the equator if they're aligned sort of correctly, so to speak. So in the upper troposphere, as you can see from this picture at the top, we have this manifestation of this anticyclonic Rossby gyres of the order of, and their size is of the order of Rossby deformation radius, which depends on stratification and scale height, as well as the change of the Coriolis parameter with latitude. However, on telelocked planets, due to their typically slow rotation compared to that to the Earth, this Rossby deformation radius is often comparable to the size of the planet, as you can see from the schematic from Schumann's review to 2013. When the Rossby deformation radius becomes comparable to the radius of the planet, we can assume that the circulation, a sort of circulation regime like that in the tropics envelops the whole planet eventually. And so many approximations and force balances become true over the whole planet. And this is a GCM simulation of a telelocked rocky exoplanets from Wang and Yang 2020. And you can see that there's also two dipoles of circulation centers. However, the phase of these stationary waves is shifted. It's kind of the opposite from the picture on the top. And this is because of the subrotation at the equator, which shifts the phase of these waves. And this kind of circulation with two Rossby lobes to the west and equatorial Kelvin wave-like structure to the east of the substellar point is quite familiar, and it has been studied extensively over the past decade and more in papers such as those presented in this slide. And I'm sure this picture is familiar to a lot of you. However, what we found is that there is a dichotomy of circulation, and in particular, we noticed that when we run simulations for the time decomparison project, we are using 4 GCMs: ExoCam, LMDG, Rocky 3D, and VUM. And these simulations were run for both dry and moist simulations, moist conditions, both for nitrogen and CO2 dominated atmospheres. And these cross-sections show the zonal mean, zonal wind in the steady state in the simulations. And you can see that there is there are of course some differences in the upper atmosphere, but if you focus on the lower atmosphere, there is also a distinct dichotomy of the regimes. In some of them, you have this classic super-rotating jet at the equator, while in others, jets split and migrate towards higher latitude. And even though there is some super-rotation at the equator still, it's much weaker than in the equatorial jet regime. And so these regimes emerge in all kinds of simulation, in all four simulations analyzed in the TIE project. So what I decided to do is to explore this peculiarity further using the Met Office unified model. And for simplicity, I'm focusing in my study on the HAB1-like setup. So this is a moist simulation with a nitrogen-dominated atmosphere and 400 ppm of CO2. And for my simulations, I'm using the same, basically the same setup as we used for the TIE simulations, which is the grid parameters are listed here on the slide. And I ran the model for 3,000 days, although I also ran it for longer, and it doesn't change the results. So in addition to the control HAB1-like simulation, so to speak, I ran a series of sensitivity runs where I changed such model parameters as convection scheme. Then I switched on and off cloud radiative effect. I changed the initial isothermal profile of the atmosphere. I also changed the slab ocean depth, the surface temperature, and initial state. So in the control simulations, I used the Gregory-Rountree mass flux convection scheme, which is the most sophisticated convection scheme in our model, and is used in many other 3D GCMs for exoplanets. The cloud radiative effect was, of course, switched on. The initial temperature was 300 Kelvin throughout the whole atmosphere and the surface. And the slab ocean depth was 1 meter. And this, because we used the slab ocean setup, the surface temperature was allowed to vary throughout the simulation, so it's dynamic. Yes, and the atmosphere was at rest. And then in these series of sensitivity runs, in one of them I switched off, or rather in several of them I switched off the, I changed the convection scheme to the convection adjustment scheme, which is much simpler convection parameterization. I also tried switching off the cloud radiative effect and then starting the model from various other initial temperatures, varying slab ocean depths, fixing the surface temperature, and also swapping the initial conditions for a spun-up circulation from a different regime to see how robust the emerging regime is. And so in all of these simulations, pretty much, all of these simulations fall into two distinct regimes. The equatorial jet regime with strong superrotation at the equator, and mid-latitude jet regime with, as it says on the tin, 2 mid-latitude jets and weaker subrotation at the equator. So, and we can also look not only at the zonal mean cross-sections of wind and temperature, but also at such key characteristics of the simulation as differential height anomalies and temperature in the mid-troposphere, as well as the wind at 300 hectopascals. And you can see that the again, the equatorial jet regime is characterized by this classic commonly obtained picture with cold Rossby gyres on the night side to the west of the substellar point, and stronger superrotation at the equator, and relatively low gradient between the equator and the poles. While here we have strong mid-latitude jets and stronger equator to pole temperature difference. And as I will discuss a bit later, you can clearly see in the gravitational height anomaly field that the planetary scale stationary waves are shifted and pretty much have mirror opposite pattern. So besides these dynamical features, we can also look at surface temperature and near surface winds. And as you can see here in the equatorial jet regime, the surface temperature is much lower on the night side and in this cold traps beneath the Rossby gyres in particular. There's also a different structure of the near surface convergence on the day side. And this drives the differences in the distribution of water vapor. So this is a total column water vapor in the two simulations, and total column cloud water. And I can also condense the results of all these sensitivity experiments and again demonstrate that they fall into two distinct regimes by showing, by plotting the latitude of the tropospheric jet and versus the maximum zonal wind at the equator at 300 hectopascals, for example. And so you can see that all the sensitivity experiments cluster into two regimes with virtually no intermediate regimes in between. You can also see straight away that there are more orange markers in the MJ regime region, which shows us that using the simpler convection adjustment scheme leads to the emergence of this MJ regime, and it's generally more robust to perturbing the modal parameters or perturbing the initial conditions, and it almost always ends up in this regime. On the other hand, using the mass flux convection scheme does not guarantee that the model simulation ends up in the EG regime, and you can see that some blue markers end up here. So in particular, 3 simulations with different initial temperature and end up in the MJ regime, as does the no cloud radiative effect simulation and also fixed SST. And this is the fact that initial conditions lead to can lead to a different regime is particularly interesting and potentially worrying feature for GCM modeling of exoplanets. And this is why in the following I'm going to explore it even further. And these two parameters are not the only ones that show this distinct clustering. We can also look at the meridional gradient of the mean tropospheric temperature on the y-axis versus the maximum zonal wind at the equator. Again, you see clustering, and then the same sort of situation is seen with the surface temperature in cold traps. These two outliers are different just because the surface temperature is fixed for the night side in the simulations, but the rest are still in these two distinct clusters, as well as other dynamical characteristics of the circulation. And and finally, what is also interesting is that there is also some sort of, to some extent, clustering with respect to the specific humidity in the upper troposphere at around 100 hectopascals. And this, as I will later show, leads to differences in the transmission spectrum. So, as I said, the key difference, dynamically speaking, between these two regimes is the pattern of stationary waves. And these are readily seen in this field of geopotential height anomalies. So this is just the deviation from the zonal mean, both in terms of geopotential height and wind velocity shown by quivers. So we can also look at this field in the vertical. So this is a vertical cross-section along the equator. So this in the middle, we have the substellar point, and it goes from the antistellar back to antistellar. And you can see that the response in the stationary waves is very different in these two circulation regimes. In the EG regime, equatorial jet regime, the stationary waves are much stronger, and they're strongest throughout the whole atmosphere, and the magnitude is the largest at around 300 hectopascals. However, you can also see that the vertical motions, which are of course exaggerated here in this quiver plot, are still much weaker than those in the mid-latitude jet regime. And you can also see that there's significant tilt in these waves, which also speaks of a different structure of the waves. And so this kind of structure is very similar to what is obtained in many previous studies that use shallow water equations. Essentially, this pattern is a superposition of stationary Kelvin, equatorially trapped Kelvin wave, and Rossby waves away from the equator. And you can also look at, you can also see this same pattern that emerges in the simulations of convectively coupled Kelvin waves. There's a good review by Kiladis et al. 2009. Essentially, this is also showing the superposition of equatorial Rossby and Kelvin waves, what we see in our simulations. And you can also check out these papers starting from classic Matsuno papers and going all the way to Wang and Yang 2021. Another good review of this of the differences in the stationary waves is given in the review by Pierre Humbert and Hammond, 2019. In that review, they show the response of atmospheric circulation in a simplified GCM to different stellar flux. So essentially, from cold to temperate to hot, which responds to the increasing insolation. And they explored different rotation rates from 10-day to 5-day to 2-day periods for a telelocked planet. And you can see in the middle row, which shows the 5-day rotation rate, rotation period simulation, which is quite close to that of TRAPPIST-1e. Indeed, a similar transition of the circulation is seen when they go from the cold to temperate to hot regimes. And it's seen both in this temperature field at 500 hectopascal, as well as the zonal mean, zonal wind cross sections on the right. But the tricky thing is, it is much more difficult to disentangle the mechanism of this transition in a full-scale GCM with all the moisture effects. Compare that to what has been done in shallow water equation models or dry idealized GCMs. Another way to look at this stationary wave fields is to look at rotational and divergent components of the flow, which can be obtained by Helmholtz decomposition, which was very well discussed in the paper by Hammond and Lewis in 2021. Essentially, what they do is they decompose the total circulation into rotational and divergent parts, and then average the rotational parts zonally, which produces the zonal jet, and the deviation from the zonal mean produces the stationary wave pattern. And it is indeed seen in our simulations quite clearly. If you compare, so first of all, this picture shows the vertical wind speed as contours and horizontal wind speed as quivers, colored quivers. And the first row shows the zonal mean rotational component, which corresponds to the superrotating jet. And you can see it's well defined here. Then the eddy part, zonal deviation of the rotational component, matches, of course, the picture that we saw in the Egyptian height. And you can see here that the Rossby gyres are sort of shifted as they are in the Egyptian height. And then we have the divergent component, which is quite different in these two simulations. It is much weaker in the equatorial jet regime and much stronger in the mid-latitude jet regime. So in the interest of time, I think I'm going to skip this, but the key point is that these different components of the global circulation, divergent, jet, and eddy, can transport the moist static energy differently, and it is this transport is quite different in these two simulations. So if people are interested, I can come back to it. So up till now, most of the studies that looked at different circulation regimes and transitions focused mostly on the steady state picture, which is justified because tidally locked planet has this stationary forcing from its host star. However, for GCM modelers, I think it's important to look at the emergence of equatorial superrotation during the spin-up of the model. And this indeed shows some differences in our simulations. The response, these transitions of and bistability of circulation on Earth and other rocky planets has been studied for a long time, all the way from, for example, by Suarez and Duffy in 1992, where they tracked the emergence of subrotation on an Earth-like planet, which responded to different magnitude of forcing at the equator. Arnold et al. Studied regime transitioned also depending on the magnitude of forcing, and they showed that there is a threshold of forcing amplitude for the equatorial subrotation, and also some bifurcation of this regime. Other papers considered not only the bifurcation, but also hysteresis of atmospheric circulation, such as this paper by Hubbard et al. In 2020, where they used a quite idealized shallow water equation model to study the response to forcing. But another interesting result was shown by Edson et al. In 2011, where they showed a hysteresis in atmospheric circulation with respect to the rotation period. However, nobody really studied the emergence of subrotation for TRAPPIST-1e, and most of other studies concerned external forcing, such as the rotation period or different installation, while in our simulations and in the comparison simulations, we saw that these transitions and dichotomy of the regimes also emerge due to different parameters and even initial conditions, as I showed. And we can look at the emergence of the planetary waves, planetary scale waves and subrotation by looking at this animation. This is an animation going from the day 0 of the simulation all the way to day 500 or 400, and the field that is shown is the geopotential height anomaly. And you can also see that there is this vertical sine line, which essentially tracks the maximum of the geopotential height anomaly. And the corresponding sine line is shown on as time series at bottom. So if I just play the animation, you can see that at the beginning, the regime is actually closer to that of mid-latitude jet regime, with sort of the phase of the waves, the maximum of the waves to the west of the substellar point. But then as the simulation progresses, in the control simulation, the equatorial jet regime emerges and the amplitude of the waves becomes much stronger, and it's gradually shifted to the eastern hemisphere of the planet, and it stays there throughout the simulation. And this is again shown by this sine line time series, where the longitude of the wave crest settles at around 45 degrees east. On the other hand, in the MJ regime, there are some significant fluctuations, but the emergent circulation settles on the mid-latitude regime, and the acceleration of the equatorial jet, which is shown by the brown line, brown time series at the bottom, is not achieved, and the shift of the wave crest is also not achieved, and it stays in the Western Hemisphere instead. Right. So, so this is the same plot again, but larger, and you can see that there's a perfect match between the longitude of the wave crest and the zonal mean, zonal maximal zonal wind and the equator. And there's a distinct difference between them. So what we see essentially here is wavejet resonance. And this wavejet resonance has been studied in shallow water models, for example, in this recent study by Wang and Yang, where they run shallow water equations for a broad range of radiative and drag timescales, as well as different background flow. And if you squint at this figure, you can kind of find a pattern that matches the equatorial jet or mid-latitude jet regimes that we have in the GCM simulations. And essentially, in some of these experiments, this wavejet resonance is achieved, and it depends on the timescales of drag and radiative forcing. And this resonance is achieved at least for the Earth-like rocky exoplanets for the atmospheres, such as those that shown in this study, is achieved because of the Rossby wave. And this is because the Rossby wave phase speed is comparable, sort of the optimal speed of the Rossby wave needed for the wavejet resonance is achievable by the zonal mean zonal flow. And as you can see, that at certain combination of radiative and drag timescales, the Rossby wave crest, which is depicted on the y scale axis here, is shifted towards the east, just as we saw in our simulations. On the other hand, the Kelvin component, the Kelvin wave, stays in the close to the substellar point and is not shifted because the phase speed is much higher, and these speeds are not achieved by the atmospheric circulation. And as a side note, this resonance, wavejet resonance, can be also thought of as an optimal conversion of energy, which is depicted here, but I won't go into detail here. You can check out the paper. And indeed, in our simulations, what I plotted here at the bottom as vertical lines are the rough estimate of the Rossby wave phase speed compared to the equatorial profiles of zonal mean and maximum wind speed. The blue lines show the equatorial jet regime, and the orange lines show the mid-latitude jet regime. And you can see that in the EG regime, at least the spatially maximum zonal wind essentially matches the Rossby wave speed, and so we can confirm that the wavejet resonance indeed occurs here, the resonance with the Rossby wave. We can also try to explain the differences in the emergence of subrotation by looking at the zonal momentum budget. But this is, to be honest, this is still work in progress, and myself, I am not convinced that this is the perfect explanation of the bifurcation. But if you look at the eddy horizontal and eddy vertical terms in particular, so shown by blue and cyan lines in each of the regimes, you can see that together with the emergence of the subrotation, or sort of slightly preceding it, the eddy horizontal component grows stronger, while it is also counteracted by the eddy vertical component, which is mostly negative throughout the simulation. And this, the eddy horizontal momentum flux due to stationary waves is what drives the flux of momentum and to the equator and the acceleration of the equatorial jet. In the MJ regime, on the other hand, there are large fluctuations at the beginning, but then this sort of resonance is not achieved, and the flux of momentum due to horizontal eddies are not is much weaker here. Next I'm going to move on to the another part of the spin-up process, namely the decrease of surface temperature on the night side in the equatorial jet regime simulation. So as you can remember from a few slides back, there's a big difference in the surface temperature between these two regimes, even given the same convection scheme, but other model parameters. So why that happens, to explore why this happens, I looked at the surface temperature heat balance in the cold traps, so averaged over the cold trap regions for both simulations. I looked at the change in surface temperature, and I also plotted the key components of surface heat balance, such as the net downward radiation, sensible and latent heat fluxes, and also the downward long wave radiation separately. And you can see, first of all, that the sensible and latent heat fluxes are minuscule. They don't really affect the change in temperature. And the main driver of the change in temperature is the net downward long wave radiation, whose curve perfectly matches the change in surface temperature. And you can see here that there's a distinct drop in the downward long wave radiation after about 150 days, just when the equatorial subrotation emerges in previous plots. On the other hand, in the MJ regime, the same term stays roughly constant throughout the simulation, that doesn't experience the same drop. So then I explored this further, and this is the same plot. And then at the bottom, I plotted the spin-up time series for the same cold trap regions by looking at and I looked at the surface temperature itself. So this is the time series of the surface temperature shown in blue. You can clearly see the significant drop in the values from around 240 to about 180 or as low as 170 in the EG regime. And this happens mostly because of the water vapor radiative effect which is shown by the solid red line here. Whereas the cloud radiative effect for the long wave radiation is a few orders of magnitude smaller and generally generally doesn't change much throughout the simulation. And this is again matches the decrease in water vapor radiative effect matches the massive decrease in water vapor path shown by the purple solid line on the left. On the other hand, in the MJ regime, these curves sort of stay, despite large fluctuations, they kind of stay roughly similar, roughly at the same level throughout the simulation. Right, and the final part of my talk is the impact on observables. So this in this plot, I'm showing the steady state transmission spectrum for the two regimes. So the blue line shows the virtual jet regime in the control simulation, and the orange line shows the MJ regime again for the sensitivity for one of the sensitivity experiments. And this is a spectrum transmission spectrum obtained from the simulation using Socrates. So it's a sort of online calculation in the model. And then what I plotted here is the wavelength range from 0.6 to 20 micrometers. Of course, you can clearly see that the differences are quite small, and they're even smaller for the clear sky spectrum. And if I plot only the differences, the differences are of an order of 1 to 2 ppm throughout the throughout this wavelength region. But there are some interesting differences at various bands. So first of all, most of the differences are between the peaks, between the CO2 peaks, while the most prominent absorption peaks corresponding to CO2 roughly stay the same, because there's enough CO2 in the upper atmosphere to saturate this this peak anyway, and it's not affected by the different regimes. But what is interesting is when we look at the east-west differences in these two regimes. So here I'm showing the same wavelength range, but this is the control simulation with the EG regime, and here I'm plotting, I'm sort of decomposing the spectrum into cloudy, clear sky, and dry contributions. And this is the same picture, but for the MJ regime. And even though the relative differences are, of course, again, small, these are the differences between the eastern and western terminators. So eastern minus western. This picture shows us that the EG regime has a bigger asymmetry than the MJ regime, and most asymmetry is due to water vapor at its absorption bands. So you can see that these biggest differences correspond to the key water vapor absorption bands, such as the 6.3 micrometers, for example. However, there's also between them, there's also differences in there are also differences in the continuum on the order of about a quarter of ppm, and this again shows that the eastern terminator is cloudier, which can be seen if we look at the mean profiles of cloud water determinators. So these plots show us that both in terms of liquid and ice water mass mixing ratio, the eastern terminator, shown by the dashed lines, has more clouds, and so the continuum is higher for that transmission spectrum. And the final note is that the temperature contribution is the smallest, unsurprisingly, and it's seen mostly in the CO2 bands and also the Rayleigh slope in the shorter wavelengths. And also interesting to note is that these east-west differences are much smaller than those reported by Sung and Yang in their recent paper, probably because they used Exocam, which is known to have higher water vapor content in the upper atmosphere and also higher clouds. So it would be interesting to use more models to compare east-west differences and possibly to try to determine if particular circulation regimes lead to differences in the transmission spectrum. So to conclude, the take-home messages are the following. So to answer the questions I posed at the beginning, several model parameters can tip the circulation into a different regime. There is significant dependence on the convection scheme. So one convection scheme is more robust to other perturbations compared to the other. Also, what is important is cloud relative effect and day-side surface temperature. So I haven't shown this in detail in this talk, but I'm happy to talk about this too. But what is most surprising to me, at least, is that initial conditions are important for our simulations, especially for the mass flux convection scheme. So I think people should take note, and modelers, GCM modelers may, well, it would be good to explore this sensitivity further and potentially, which potentially can affect the model setup in our in all the intercomparisons and so on. So generally speaking, the mechanism of regime bifurcation is the differences is the momentum transferred by stationary eddies, and in certain regimes, it looks like the stationary eddies can be disrupted, and this momentum transport weakens. Therefore, it doesn't produce enough equatorial superrotation, and instead, most of the zonal momentum is transported by the mean circulation to the mid latitudes. And the very low night side surface temperature in the equatorial jet regime is caused by a large decrease in water vapor, and as a result, a reduction of the greenhouse effect. And so the water amount of the in the upper atmosphere is also affected, even for simulations with the same convection scheme. And it affects the observables to some extent, but of course it's much smaller than the noise level of JWST, for example. So to observe that, we need the next generation of telescopes, I guess. So this work will be soon submitted to the Planetary Science Journal TIE special issue, I hope. But any feedback, any comments are very welcome. Thank you for your attention.
Thank you very much, Denis. That's really, really super interesting. That planet is really fascinating because I don't think we have another exoplanet like that where we can have such dichotomy.
It's a tricky planet. Yeah.
Yeah. Do we have any questions? Not yet. Okay, I'm going to start with one. So what do you think the part is the stellar energy distribution? We have a very red spectrum is TRAPPIST-1. What do you think is the part of this stellar energy distribution play into the dynamical regime and even the dichotomy you can have depending on your initial condition? Like if you will really fix everything the same, but you will get the stellar energy distribution from the sun, you will scale the insolation to match, you know, the warming effect. Do you think you will get similar results or?
Sorry, distribution of what?
The stellar energy distribution, the fact that
right.
the spectrum of TRAPPIST-1 is really shifted toward the red, the infrared.
Yeah.
What do you think this, you know, plays into that effect?
Yeah, so that's a very good question, and this is one thing I also want to explore, maybe in a future work in more detail. But you know, generally speaking, as some of my simulations show, the cloud radiative effect is very important, and if you don't have it, the circulation just immediately settles on this mid-latitude jet regime.
Mm-hmm.
So depending again what condensable you have, if it's water, you know, it has a different radiative effect for a redder stellar spectrum, and so I think that also is a very likely candidate to just shift the circulation, at least for TRAPPIST-1e. Yeah.
Okay, cool. Thank you. Any question?
While people are asking, I'm also gonna show the some of the some work that is done within ETG, just to be on the slide. Yeah.
Okay, we have a question from Avi first, and then Mike.
Mm-hmm.
Yeah, thanks, Denis. Great talk overall. I'm interested, of course, in the observables. And one of the biggest challenges for accurately sort of predicting transmission spectra is the upper atmosphere and the contribution from sort of vertically distributed, whether it's aerosols or haze or your molecular abundances or outflows or all of these types of things, which of course are challenging to match with the GCM, the base of the atmosphere. How does the MET model handle this sort of transition? And do you think that, I mean, obviously you're getting some good spectra here, but do you think they're, how accurate, I guess, or sort of do you think there could be concerns about whether this is actually what the transmission spectra would look like in that sense?
Yeah, that's a good question. Thank you. So as far as I know, at least the spectra that we can calculate sort of online using the radiative transfer code within our model, and as well as can Rocky 3D presumably which uses Socrates as well. The Socrates works in the way that it sort of extends the highest level to 0 pascals, so to the top of the atmosphere, and in that regard, I think in the model lead placement in our simulations is not important, because at least for Earth-like atmospheres, the most of water vapor and cloud water is concentrated much lower. So the differences in the very high atmosphere is not that important. And I think the transmission spectra would be quite reliable in that sense. But it would be interesting also to use our output and put it through PSG, for example, and compare what it looks like. But yeah.
Yeah,
sorry,
I'm also thinking I'm also thinking of those other factors that take hold at the top, when you get into, diffuse media where you could have different chemistry or different, sort of dynamics that are not necessarily driven by, the same sort of convection dynamics. Anyway, any of these other factors, I know there's these unknown unknowns, and I don't expect you to, have the full nuts, the soup to nuts here, but I'm just wondering if, I mean, I know, for example, I've heard some, folks, other GCM folks start talking about, well, we might need to link this, 1D or other types of models or chemistry or other types of things with the base dynamical model in that sense. So.
Oh, yeah, that's a good point. And yeah, as you know, it's a broad field and it's still not explored enough. And in our model, the short answer is that we don't take into account all the weird effects like non-LTE effects and stuff like that. But we recently have been improving the sort of upper atmospheric treatment of radiation with including photolysis, well, updated photolysis in Socrates and in the And I think there is some development at the Met Office with regards to sort of mesosphere and sort of space weather prediction. So yeah, thanks.
Mike, you have a question?
Yeah, I thought first I would pick up a little bit on what Avi was saying there. I think Dennis probably stressed it, but that's the beauty of this study is we have a bunch of different GCMs that can tell us, well, something. We don't, I mean, I read things sometimes quite funny. People say, well, this study is going to tell us which GCM is right, which is which is kind of comical, really. But at least they can tell us where our weaknesses are. And I thought that, unfortunately, I missed part of the discussion that you had about the initial conditions on the mass flux scheme, which is a bit troublesome. But I just want to go back to that for a second, even though I missed it. But one thing that I had a discussion with Martin about was the fact that, for example, in Rocky 3D, we had really low speed zonal winds in the upper atmosphere compared to other GCMs. I don't know if you were on that discussion or not, but it's in your plots actually. But it turned out, we all are using different kinds of stratospheric drag parameterizations or approximations. We use some in particular because we get instabilities in the upper atmosphere, which is why we all have sponge layers up there, of course, and things like that. And those different treatments can have large effects. In this case, you can see in the top right panel for Rocky 3D, it's very low compared to the others. So I don't know if that also plays a role in the convections, in what the convection scheme outputs in a sense, because if your winds are quite low, that I could see that affecting how convection operates, especially in the upper atmosphere. So I don't know what your thoughts on that were, but do you see them being coupled in some way? Do you think that if we ended up with the same drag parameterizations, we would see the same? I just wonder if there's some connection in other parts. This thing's so complex. I think it's admirable you're trying to disentangle everything, but it looks extremely hard, as you know, to get there. So I'm rambling on. I'll let you talk a bit.
Thanks, Mike, for the question. Yeah, I mean, amen to that. Yeah, it's very hard to disentangle this sort of, what drives what in the GCM. But I think with regards to upper atmosphere, I'm not sure that the circulation itself would matter for this bifurcation that I'm studying, because I'm focusing on the lowest part of the atmosphere, sort of below about 10 kilometers. And so from my simulations, at least I get a sense that it's not really coupled, and sort of the regime clustering in the lower troposphere is not very correlated with what happens, what jets emerge at the top of the model. But I think it might have an effect if we look at the sort of temperature profiles like this, but maybe over the substellar point, because of course then this temperature profile, like it would affect the strength of the convection and where it's triggered. So yeah, the short answer is I'm not sure.
No, that's cool. It's a perfect answer, actually. Yeah, okay. I like I said, I missed a little bit, so I didn't realize you were focusing on the lower stuff. That makes sense in the convection sense, but definitely these winds in the upper atmosphere are going to affect temperatures. There's no doubt about it, because you're convecting heat away, right? And if you're not convecting heat away, you're going to get different temperatures. That makes complete sort of intuitive sense, right? But this is really great stuff, Dennis. Thank you so much. I really enjoyed this. I think we should. I'm going to try to set up a talk for you at GIST, because I think some of the climate people would enjoy some of this stuff, because we don't often talk about these things at a fundamental level.
Yeah, that would be great. Thank you.
No worries.
Thank you. Yeah, it was a very interesting question, and I think also the problem, as you know, is like the drag coefficient are very important for the stability of the model right there, and so it's difficult to fix the same value for all the models. But
yeah.
Well, actually, we just said very quickly, I use the same ones in all the models, because some are more stable, some are unstable and need them, and some don't. And I just thought, I'll just use the same ones for all of them. But then when Martin came to me with this question, it turned out I didn't need them for the TRAPPIST. This very stable regime I put in, this Rayleigh drag we put in, it's really strict. And so when I turned all that off, things started looking like other models quite nicely, as you might expect.
I've actually started to reproduce tie simulations in the next generation modeling system of the Met Office, the ELFRIC model. And I also noticed that the equatorial subrotation and the upper atmospheric winds are very low, and the picture that emerges in, at least in the BEN1 and HUB1 simulations of tie, is actually quite similar to that of Rocky 3D. So yeah, I hope to explore it further, maybe report on that next time.
Yeah, and I just, if it's okay, I just want to mention one other thing, is that I've been having some students compare some simulations we've done to this intercomparison that Jun Yang did a few years before, and where he did kind of funny things. I'm realizing now, turning off sea ice and turning off clouds in the model. And I think in hindsight, that was a really not the best way to compare the models, because I see all kinds of weird behavior in our model when we do that, because everything's so coupled. And to turn something off and not understand what else it's coupled to, I think that intercomparison study is almost useless. It doesn't, it's really hard to know what you've really done to your model when you just turn off one component, which is so deeply coupled in ways that the people turning it off don't understand. Because these are Earth parent models, and the guy or girl that wrote the code isn't around to tell you, don't ever do that.
And then you have the knock-on effects in the rest of GCM, which usually kind of tuned to everything is turned on, and then it all falls apart.
I just wanted to give kudos to you and Toma and others for putting together a much more intelligent intercomparison, where we set up the initial conditions in a way where we didn't have to turn off all these interdependent variables. I mean, doing a very dry planet turned out to be a very smart way to look at things that they were trying to do, but in a more intelligent way. So kudos to you guys.
Thanks, Toma.
Of course, thank you too. Thanks to you, Mike, as well. All right, it's 12:13 here. Time to wrap up. Again, thank you very much, Denis. That was really a super interesting talk. And thank you for all the participants. A few of them remains now. But yeah, we will see each other, I think, in a few weeks for the next Exoplanets seminar. Have a good one, everyone.
Everyone.